Good afternoon, everyone. I feel a great honor to be here to share my study with you. Thank you for giving me the chance, and I hope this can be a good presentation. My name is Lingling Huang, and I am a PhD candidate at Southeast University. Today, the title of my study is Plasma Proteomics Analysis of Early Biomarkers for Predicting Female Fecundability, a nested case control study. In the following 30 minutes, I will share your study from these aspects. As we all know, identify is a global public health issue. On April 3rd, 2023, WHO released a report of infertility prevalence estimates, which shows that the global lifetime prevalence of infertility was approximately 17.5%, with a paired prevalence was about 12.6%. The report also noted that there are regional differences in the prevalence of infertility. The highest lifetime prevalence was in the Western Pacific region, followed by the Americas, and Europe with the lowest in the Eastern Mediterranean region. The highest current prevalence was in Africa, followed by the Western Pacific and Europe with the lowest in the Eastern Mediterranean. However, the prevalence of infertility was almost the same across countries with different income levels. While in China, it is estimated to be 15 to 20%, and it has been increasing year by year. Infertility affects 25% of couples of reproductive age, causing significant psychological and social pressure on both partners. Approximately 35% of infertility cases are caused by male factors, while 45% are due to female factors such as endometrial abnormalities, irregular menstruation, PCOS, follicular dysplasia, and fallopian tube gene. Currently, female fecundability is typically diagnosed through sex hormone tests, hysterosalpingography, ultrasound-based antral follicle count, carrier typing, and gynecological tests. However, these diagnostic tests are required to be performed during the menstrual period of women and have a high cost. Additionally, ultrasound exams can be uncomfortable or painful for women who have not had sexual experience, making them difficult to accept. There are also limiting non-invasive biomarkers available for monitoring fecundability. Plasma proteomics analysis is considered a rapid and non-invasive method with a high potential to predict female fecundability levels. In recent years, plasma proteomics techniques have been widely used to predict virus diseases. For example, Chu constructed a predictive model to differentiate patients with muscle invasive and non-muscle invasive upper tract urothelial carcinoma. In predict the possibility of fetal congenital heart disease by early pregnancy. Plasma proteomics. Baca used maternal plasma samples at 3 months of pregnancy to confirm proteomics-based differences between pregnant women with preeclampsia and normal pregnant women, and one used maternal plasma samples in late pregnancy to predict the occurrence of preeclampsia. Afterman found that the application of plasma proteomics analysis can accurately predict the possibility of adverse pregnancy outcomes in pregnant women with PCOS. And therefore, we propose a plasma proteomics based method for the first time to detect and identify characteristic protein biomarkers in low fecundability patients. We analyze the plasma samples by using mass spectrometry-based DIA quantitative proteomics, plasma proteomic profiles of pregnant and non-pregnant women were generated. Then we elucidated and verified characteristic proteins by WB, ELISA, and biochemical tests. The study is a register-based nationwide cohort study and with participants enrolled in the NFPCP from 2015 to 2018. We conducted a nested case control study involving couples who participated in the project to determine the association between the plasma protein levels of women and their fecundability. The inclusion and exclusion criteria were as follows. After entering the study, women who successfully conceived within 1 year were defined as a high fecundability group, while those unable to conceive were defined as a low fecundability group. For the training cohort, plasma samples were obtained from the HF group and LF group for proteomics analysis and complied with the guidance of Human Protein Organization's Proteomics Standard Initiative for reporting proteomics studies. For the validation cohort, plasma samples were obtained from the HF group and the LF group and used for sequent biochemical and molecular bioassays. PC analysis revealed two significant clusters in all of the identified proteins. Then we identified 3,904 and 3,820 proteins expressed in the HF and LF groups in the training cohort, respectively, and 2,969 proteins were commonly expressed in both groups. Following sample data cleaning and analysis, we identified 182 depths between the HF group and the LF group, including 102 up-regulated and 8 down-regulated proteins. The depths were then clustered into 4 modules by K-means analysis using the PPI network. KGG pathway enrichment analysis showed that a significant number of upregulated depths were enriched in pathways related to glycolysis, neogenesis, carbon metabolism, and metabolism. We selected 4,951 proteins and 10 clinic traits to generate a protein co-expression network using WGCNA. 70 modules were identified, and each module was assigned a different color. The model-trait relationship analysis suggested that the black module was positively associated with the female TSH level, and the magenta module was negatively associated with the male creatinine level. The turquoise module and the purple module showed positive relationships with the female ALT level and the female AST level, respectively. Additionally, positive correlation also existed in the red module and male BMI as well as male creatinine, and the pink module and the age at menarche as well as the female BMI. Then in the turquoise module, 46 overlapping proteins were found between WGCNA and DAPS. Among them, the PKM protein was related to the glycolytic pathway, demonstrating its importance in fecundability performance. The RC curves of the proteomics data in the training set were used to predict the diagnostic efficiency of depth for fecundability. Depths with significant enrichment in KGH pathway were selected for prediction. LDH2, DCXR, GSTP1, L3HY, PDH, ATP6V1A, and PKM2 exhibited a significantly higher diagnostic efficiency for fecundability prediction. The AUC value of PKM2 was 0.81. These proteins were mainly enriched in metabolic pathways and glycolytic pathways. The analysis of depth revealed that proteins involved in the glycolytic pathway and metabolic pathways showed a high expression in the HF group as compared to that in the LF group, such as DLST, ALDH2, ALDOC, IDH3A, and PKM2. To obtain reliable results, we conducted the Western blotting assay to validate the abundance of these proteins and other proteins with a significant alteration in expression in samples from the NFPCP group as a test data set. The results confirmed the increased expression of PKM2, ALDH2, ALDOC, IDH3A, and DIST-ER and GAPDH is in the plasma samples of the HF group as compared to that in the LF group. A finding that was consistent with the proteomics analysis results of the training data set. In addition, the pyruvate level of was significantly increased in the HF group with an AUC value of 0.68. The two groups, however, showed no difference in the plasma expression level of estradiol, LDH, G6P, and lactate. The levels of pyruvate was assessed as a continuous and categorical variable. The first total participants were used as a reference group. The univariate analysis showed that compared to the T1 group, the hazard ratios of fecundability were 2.40 in total 2 and 3.1 in total 3 with a significant trend test. After adjusting for age as a confounding factor, we found that compared to the T1 group, the hazard ratios of fecundability was 2.69 in total 3 with a significant trend test. After adjusting for the female ART level, female AST level, female creatinine, and female TSH level as a confounding factors, we noted that compared to the T1 group, the hazard ratios of fecundability were 2.84 in total 3 with a significant trend test. Additionally, after adjusting for male age, male BMI, male ALT level, male AST level, and male creatinine as confounding factors, we observed that compared to the T1 group, the hazard ratios of fecundability were 3.82 in total 3 with significant trend test. The RCS model showed a linear positive dose response association between the pyruvate level and the prevalence of fecundability among the subjects. The hazard ratios value for fecundability increased with an increase in the pyruvate level, particularly when the pyruvate level was higher than 0.23 mmol per liter. The study confirmed that plasma proteins are beneficial in predicting low fecundability. The plasma expression level of PKM2, ALDH2, ALDOC, IDH3A, DLST, ER, GAPDH, and pyruvate were significantly lower in infertile women than in women with a shorter TTP who had a great likelihood of conceiving. Thus, the downregulation of these proteins indicates a poor pregnancy potential. In particular, the RC-CAF analysis confirmed that PKM2 could serve as a potential biomarker to predict fecundability, and the Cox proportional hazard regression model and the RCS analysis showed the linear positive correlation between the paravet level and fecundability. In the present study, proteomics analysis was used to discover and confirm differences in the levels of glycolytic pathway-related proteins and paravet among women with different fecundability levels. We proposed a new structure to predict female fecundability levels based on proteomics analysis for the first time. This structure is not limited by the requirement for specialized invasive testing methods, and the samples are available. It provides a personalized fecundability assessment for women and promptly identifies women with low fecundability levels, thereby with low fecundability thereby providing a more reproductive time window for couples preparing for pregnancy and enable them to adopt appropriate intervention measures to improve the fecundability level of female partners. Also, the conclusion of the study provides a sufficient theoretical basis and experimental verification. The study still has some limitations. First, the number of women included in plasma proteomics analysis was relatively small, resulting in the lack of representativeness in study conclusions. In further studies, we plan to expand the sample size and use larger cohort to validate our conclusions to determine whether the levels of biomarkers can accurately predict the likelihood of pregnancy. Second, protein sequencing technology has certain cost-effectiveness issues. High sequencing cost and highly specialized requirements for sample preparation, dashing processes, and data computation, thus making it difficult for sequencing methods to provide benefits to the general public. Third, proteomics results may vary among individuals from different races, countries, and ethnicities. Moreover, they may be influenced by the psychological status of women, environmental factors, lifestyle, and other factors. However, the present study included only women from Gulou district, Nanjing province in China, who were preparing for pregnancy in the NFPCP group. A single sample source was used. Therefore, in sequence studies, we plan to include women of childbearing age from different races, countries, and ethnicities, and consider interference of multiple factors to obtain more rigorous and reliable conclusions. First, lifestyle changes may have potential impacts on plasma proteomics, such as changes in dietary habits, increase physical activity, stress management, smoking cessation, and alcohol restriction lifestyle adjustments. These changes may indirectly affect fecundability by affecting hormone levels, inflammatory reactions, metabolic process, and other pathways. In next step of our research, we will collect detailed lifestyle data to control for potential confounding variables by adjusting the effects of these variables through statistic models, such as multivariate regression analysis. We can more accurately estimate the association between changes in plasma proteomics and fecundability. Next stage, we plan to design a longitudinal study to track the entire process of women from preparing for pregnancy to successful Nancy observes the dynamic changes to differential proteins at different stages and verifies their effectiveness as early fertility prediction indicators. We will conduct deeper mechanism research to explore the specific biological roles of these differential proteins in female fertility. In summary, although plasma proteomics technology has some limitations to predict female fecundability levels, it also has apparent advantages to better utilize this technology to predict female fecundability levels. Further research and large-scale validation studies are required to enhance this credibility of our research conclusions. In the end, I would like to express my sincere gratitude to the WNHS for providing me with the opportunity to present my work. And I am also deeply thankful for the support from IFPCP under the National Health Communications Institute. And thanks for the National Natural Science Foundation of China for the financial support. Thanks for the research platform provided by Southeast University. Thanks for the assistance from MCH Plus team. Thanks for your listening. And if you have any question, please you can contact my email. That's all. Thank you.